Hello and welcome. In this video, we're going to learn about independent and dependent events. Our goals are that we can determine if events are independent and find the probability of independent events, and that we can determine if events are dependent and find the conditional probability. Let's go ahead and jump in. Let's start by defining independent and dependent events. Two events are independent if one occurring doesn't affect the other occurring. So if I roll a die and I flip a coin, what happened when I rolled the die doesn't affect what would happen when I flipped the coin. As opposed to dependent, two events are dependent events if the occurrence of one does affect the occurrence of the other. So for example, if I was looking at a deck of cards and I took a card out of the deck and I didn't put it back in the deck, that would affect what could possibly happen the next time I draw a card. The probability of event B occurring, given that event A occurred, is called the conditional probability. So if we have dependent events, then we can use this notation, probability of B given A. That's how we would say this out loud. Let's actually write that down. There we go. So we would be able to use this notation to establish that we have two dependent events and that the probability knowing that A happened actually affects what will happen when we look at B. So those are the three key definitions: independent, dependent events, and then conditional probability. Now that we've laid the foundation, let's look at what that probability, how we would find that probability for each of these types of events. All right, let's start with independent events. If two events are independent, then to find their probability, the probability of both of them happening, probability of A and B, you would just take the probability of A and the probability of B, and you would multiply them together. So for example, if we were thinking about flipping a coin twice, the probability that we flip heads and then heads would be, what's the probability of flipping heads? 1 out of 2. And the probability of flipping heads the second time, 1 out of 2. So that probability would be 1/4. We would look at each of their probabilities separately and you would multiply them together because flipping a coin is an independent event. Now this is different if we start talking about dependent events. If two events are dependent, then we would multiply the probability of the first one happening by the probability of the second one, knowing that the first one happened. So if we wanted to look at an example of dependent probability or conditional probability, we would need to look at something like a jar of marbles. Let's say that we had a jar of marbles and it actually only had 5 marbles in it, and 2 of them were red and 3 of them were blue. There's a visual for us. So let's say we didn't put a marble back and we were looking for the probability that we had blue and then that we had blue again. So if we're not putting a marble back, at the beginning, the probability of drawing a blue one is 3 out of 5 because there's 3 blue marbles out of the 5 marbles that are there. But if we take one of those marbles out, now we don't have 5 anymore, we only have 4, and we don't have 3 blue anymore, we only have 2 blue. So that is going to affect, notice how these denominators are changing. So if we simplified this, probability of blue then blue, 2/4 is the same as 1/2. And if we multiply the numerators, we would get 3, and multiply the denominators, we would get 10. So the probability of drawing blue and then blue, if we don't put the marble back in, would be 3 out of 10. And that would be a conditional probability. The probability that we used to find the second blue is dependent on the fact that we know what happened to start with. So let's really dig into this more with a bunch of examples. So for our first example, we're going to look back at a problem that we looked at in 1.1, where a student was taking a true-false quiz and randomly guessing on the 4 questions. So if you remember, if you look back, we had the example of like you could get all 4 answers incorrect, or you could get all 4 answers correct, or any combination of those. And in that section, we actually figured out that there were 16 possible outcomes on what could happen if you are guessing in terms of how many questions you get correct and incorrect. So question A is asking us to use that sample space from 1.1 to determine whether getting question 1 correctly and getting question 2 correctly, whether or not they are independent events. So conceptually, if we think about this, it really shouldn't matter if I am guessing and I'm not doing anything. It shouldn't matter if I guess question 1 right. That shouldn't affect whether or not I guess question 2 right. But let's look at the mathematical foundation for that. If these 2 events are independent, that means that we would just multiply There are two probabilities together. The probability of getting question 1 right times the probability of getting question 2 right. So what that means is if we know A, or if we know that we got question 1 right, that these two things will actually be the same. If they're independent, knowing that we got question 1 right doesn't impact getting question 2 right. So these two probabilities would be the same. So let's actually look at this in terms of the sample space that we used in 1.1. So first things first, the probability of getting number 1 correct. If you look at that list, of the 16 total outcomes, 8 of them have you getting number 1 correct, which I'm going to simplify that fraction to be 1/2. The probability of getting number 2 correct, looking at that sample space again, of the 16, 8 of them have number 2 correct, and that simplifies to be 1/2. And this should make sense. There's two options. Either you get it right or you get it wrong, and incorrect or correct. And these two probabilities both being 1/2 makes sense. So if we're saying that they are independent events, the probability of 1 and 2 being correct would be 1/2 times 1/2, which is 1/4. Now looking back at that sample space from 1.1, look at how many of the 16 had both number 1 and number 2 correct. So how many of the 16, looking back, there are 4 out of 16 that had both number 1 and number 2 correct. It would look like that. And that simplifies to be 1/4, which is what we just calculated here. So since the probability of number 1 and 2 correct is equal to the probability of number 1 correct times the probability of number 2 correct, these events are independent. And let me rewrite that so it fits nicer up there. So part B is asking us to compare it to the conditional probability that I was sort of referring to before. And it says, suppose that you know you got number 1 correct. Suppose we know that number 1 is correct. Does that impact the probability of getting number 2 correct? So what we are looking at is the probability of getting number 2 correct given that we got number 1 correct. So looking back at that sample space from 1.1, look and identify how many did we know that number 1 was correct on? How many did we know? And if you look at that, there are 8 outcomes where number 1 was correct. So here's one example of those 8 outcomes where we had number 1 being correct. Of those 8 outcomes, because that's what we know, given that number 1 is correct, what's the probability that number 2 is correct? So if we look at those 8 outcomes, how many also have number 2 correct? So how many start with CC? And then it could be II or CC, IC, etc. But how many of them have 2 C's out of those 8 that have a C first? And there are 4 of those. And this is going to simplify to be 1/2. And if we look back at part A, the probability of getting number 2 correct was 1/2. So what we're saying is that the probability of getting number 2 correct, knowing number 1 is correct, and the probability that number 2 is just correct regardless of number 1, those probabilities are both 1/2, which means that those are independent events. This is not conditional probability. And let's go ahead and write that in a sentence so that we're making sure we're clearly answering the question on part B. So just to recap again, since the probability of 2 being correct given 1 was correct is equal to the probability of number 2 being correct, our answer in part A would not be impacted, and the probabilities are independent. Let's look at a different example. All right, example 2. A group of 4 students includes 1 9th grader and 3 10th graders. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. So I'm going to use purple for speaker, and I'm going to use green for recorder. And since I don't want to write out the words 9th and 10th graders, there's only 1 9th grader. So I'm going to let 9 be the 9th grader. And I'm going to let A, B, and C represent 3 different 10th graders. And I'm going to go ahead and write that down. There we go. So this is going to make it easier when I'm listing out my sample space. But basically I'm saying 9 represents one person that happens to be a 9th grader. A represents one of the 10th graders. B represents a different 10th grader. C represents the last 10th grader. So for part A, we're just being asked to write our sample space. So one example is that we could have the 9th grader be the speaker, and then we could have 10th grader A be the recorder. So go ahead and pause the video and list out the sample space. So hopefully you had enough time to list those out, and maybe yours looks a little bit different than mine. But what I can see here is that there are 12 different outcomes because it says that we're using a different student for each thing. Someone can't be the speaker and the recorder. So I'm going to use this 12 outcome sample space to answer questions B and C. So part B says, determine whether randomly selecting a 10th grader first, and then randomly selecting a 10th grader second are independent events. So we're looking at the probability of selecting 10 and 10. And I actually want to just rewrite this over here from the previous part of these notes. If two things are independent, then we can multiply their probabilities together. That should be the same as if we look at B given A, which is what happened in our last example. So let's look at the probability of having a 10th grader and a 10th grader. So a 10th grader in both spots. And we can look at our sample space to do this. So 10th grader and 10th grader would mean I have a letter then a letter. So here, here. So of the 12 outcomes, 6 of them have 10th graders in both spots. Of the 12 outcomes, 6 of them have 10th graders in both spots. And then we're going to simplify that fraction to be 1/2. So 1/2 is the probability of having a 10th grader for both spots, for the recorder and the speaker. Now, that's looking at our sample space. If we look at the probability of one event at a time, so the probability of getting a 10th grader, well, there are 4 people that we are picking from. Of the 4 people, how many of them are 10th graders? 3 of them. So the probability of picking a 10th grader from the group of 4 that we're looking at is 3/4. Which means if we were talking about 2 independent events, the probability of getting a 10th grader for both would be the probability of having a 10th grader times the probability of having a 10th grader. If these are independent, then these probabilities are the same. And when I multiply them and simplify, I should get 1/2. And let's see if that is in fact true. Well, that would give me 9/16, and 9/16 is more than 1/2. So these 2 events are not independent events. They are dependent events. And there's our conclusion. Now, I want you to just think about, I'm going to use this space and then I'll come back to it. If I just asked you, without looking at the sample space, to find the probability of having 2 10th graders, going back to this, we know the first 10th grader has 3 out of 4 chances. But if I wanted to find the probability of the second one, knowing that we already picked one, now we only have 3 people to pick from, right? Let's pretend we picked A first. Now we only have 3 people to pick from. And of those 3 people, only 2 of them are 10th graders. And if we look at this probability, this ends up giving us 6/12, which is 1/2. So we could calculate that probability knowing that we took 1 away from the numerator and 1 away from the denominator to find the second probability. So that wasn't the focus of problem B. I just want you to see we don't necessarily need the sample space to do this. It's just nice to have it so we can refer back to what we learned in 1.1. Part C is really similar to part B. So I actually want you to pause the video, use part B as your model, and see if you can determine if these 2 events, getting a 9th grader after getting a 10th grader, if those are dependent or independent events. Then unpause the video and see how you did. All right, so the probability of getting a 10th grader and then a 9th grader, based on our sample space, there are 3 out of the 12 outcomes that have this, which is 1/4. If we look at the probability of getting a 10th grader, which we already established on part B was 3/4, and the probability of getting a 9th grader, which there's only 1 out of 4, and if we multiply these 2 probabilities together, which is what we would do if these were independent, we would have 3/4 times 1/4, which is 3/16, which is not the same as 1/4. So again, these probabilities are dependent. And there we have written up that answer. Something really important to note is that because we have to pick a different student for each role, one thing is always going to affect the other in this particular circumstance. When we start talking about decks of cards, we'll call this replacement. Since a student can't be replaced as an option for the second, knowing the first will impact the probability of knowing the second. And that's what we defined a dependent event to be. Let's go ahead and look at another example. Now that we've talked about dependent and independent events, let's focus on just finding the probability looking at a given situation. So for number 3, we're given that we're using this spinner as a part of a board game, and we're told that each of these 8 spots are equal in size. So part A says find the probability that you get a 5 on your first spin and that you get a number that's greater than 3 on your second spin. So a 5 on your first spin and a number greater than 3 on your second spin. If I spin the spinner, that doesn't affect what happens the second time that I spin the spinner. So what I mean by that is the probability of getting a 5 and then getting a number that's greater than 3 should just be equal to the probability of spinning a 5 times the probability of spinning a number that's greater than 3. So the probability of spinning a 5 is, out of the 8 total spots, only one of them is a 5. The probability of spinning a number greater than 3, out of the 8 total spots, how many of them are greater than 3? 4, 5, 6, 7, 8. So 5 of them are greater. So the probability of spinning a 5 and then spinning a number greater than 3, multiply across the top, multiply across the bottom, that probability is going to be 5/64. And if we wanted to grab a calculator, we could see that that is 0.78. Why don't you go ahead and pause the video and work through part B. So the probability of spinning an odd number twice is going to be the probability that you spin an odd number on the first one times the probability that you spin an odd number again. Well, out of the 8 numbers, 4 of them are odd. So the probability of odd then odd is going to be 4/8 times 4/8. And I just want you to notice these are both 1/2. 1/2 times 1/2 is going to be 1/4. So the probability of spinning odd and then odd is going to be equal to 1/4, which we know is 0.25. Let's go ahead and look at another example. All right, here we go. A bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. So this means we are not replacing the bill. If there is no replacement, that means we're going to be looking at dependent events. So this is going to lead us to the dependent or the conditional probability. So we are looking for the probability of A and B. So the probability that the first bill is a $100 bill and that the second bill is a $100 bill. We are going to need to use the conditional probability formula, which I'm going to go ahead and just rewrite here. So in this bag, there are 20 $1 bills and 5 $100 bills. So there's 25 total bills. I'm reaching my hand in the bag, I'm grabbing a bill. So the probability of A, the probability of grabbing a $100 bill, the first one, is out of the 25, there are 5 of them. 5 out of 25, which when we come down here, I'm going to simplify this to just be 1/5. Now, for the probability of B knowing A, first thing we know is that we now only have 24 bills in the bag because I just took one out. The one that I just took out was one of the 5, so there's only 4 more $100 bills left. So 4 out of the 24 that are left. And that fraction is going to go ahead and simplify to be 1/6. So the probability of A and B is going to be 1/5 times 1/6, which is 1 out of 30. Go ahead and pause the video and try and work through part B on your own and then unpause the video and see how you did. Hopefully you gave yourself enough time to work through this. The probability of drawing a 1 and then a 1 is the probability of 1 times the probability of 1 given 1. Of the 25 bills, 20 of them are $1 bills. So our first pick, we have 20 out of 25 chances. Our second pick, since we drew 1, we only have 19 left and there are only 24 left. We can simplify our fractions, and actually we can simplify a little bit more before we multiply. 4 goes into 24 6 times. So this probability is going to be 19 over 30. So big things to notice here, because we were not replacing the bill that went in, that makes these dependent events, which means we need to use the conditional probability formula. Let's look at some more examples. All right, for number 5, we're going to be looking at a standard deck of cards. And if you're not familiar with a 52 card deck with the 4 suits, I put a visual in our class drive, so you can go ahead and pull that up while you're looking at this, or you could Google what does a normal 52 card deck look like, so that you can understand what we're talking about when we're talking about face cards or hearts or diamonds. So we are being told that we are randomly selecting 3 cards from a standard deck. For part A, it says, what is the probability that all 3 cards are hearts when you replace each card before selecting the next card? So what that means is we're looking at the probability that we get a heart, and then another heart. But also, out of the 52 cards, each time we're always putting that card back. So our denominator isn't going to change each time we're doing that. So of the 52 cards in the deck, 13 of them are hearts. And this actually is going to simplify to 1 over 4. 13 out of 52 is the same thing as 1/4, which should make sense. There are 4 suits in a deck of cards. And if we multiply this out, we're going to get 1 out of 64 as our probability of drawing 3 hearts. All right, for part B, we're going to look at the exact same problem, except this time we are not going to put the cards back each time. So the probability of heart, but knowing that each time we're going to have fewer cards because we're not putting the card back in the deck. So the first time we pick a card, we'll have 52, then we'll have 51, then we'll have 50 cards. So of the 52 cards, 13 of them are hearts. Assuming that we picked a heart, then the second time we draw we'll only have 12, and the third time we draw we'll only have 11. So go ahead and simplify your fractions before you multiply, and then see what your final answer is going to be. And there, 11 out of 850 is the probability of drawing 3 hearts in a row if we don't put a card back in the deck. All right, I'm going to encourage you to pause the video and work on C and D on your own, and then unpause the video and see how you did. So hopefully you had time to at least work through part C, the probability of not having any hearts. Well, there's 13 hearts, so there's 39 cards that aren't a heart, 39 out of 52, and you're going to multiply that by itself 3 times since we're replacing on part C, and that probability is going to be 27 out of 64. And for part D, if we are not replacing, both our numerators are going to go down by 1 each time, as are our denominators, and then our final answer is going to be here. Let's look at 2 more examples that are formatted in a different way, but really that are still just focusing on our ability to deal with probability. Okay, on these last 2 examples, I'm going to encourage you to read through them on your own and pause the video and see how you can do, and then unpause the video to follow along with me. A quality control inspector checks for defective parts. The table shows the results of the inspector's work. So we can see how many are defective. It looks like there are a total of 39 that are defective and a total of 461 that are not defective. And then we're being asked questions about whether or not they pass or fail the test. So find the probability that a defective part, so knowing that it is defective, there are 39, passes. So what we want to know is the probability that we have a defective part that passes. So of the total defective parts, 39, how many of them pass? 3. So that probability is 3 over 39, or 1 over 13. Part B says find the probability that a non-defective part fails. So there are 461. So probability that a non-defective part fails. Of the 461 non-defective parts, how many of them failed? 11 of them failed, so that's going to be 11 over 461. Let's look at one more example. Again, pause the video, see if you can work through it on your own, and then unpause the video and follow along with me. All right, here we go. At a school, 60% of the students buy lunch, 10% of the students buy lunch and buy dessert. What is the probability that a student who buys lunch also buys dessert? So I'm going to define some things as A and B here to make our lives easier. I'm going to let A be that a student buys school lunch and B be that someone buys dessert. So we are looking at the probability of a student who buys lunch. So this is given they buy lunch. How many also buy dessert? So what we want is the probability of B given A. So remember that the probability of A and B is equal to the probability of A times the probability of B given A. And we actually know the probability of both. The probability of both is 10%. We also know the probability of A. The probability of A is 60%. And what we're looking for is this piece here, the probability of B given A. So what we're saying is 10 equals 60 times something. So to solve for the probability of B given A, we're going to divide both sides by 60, and that's going to give us 1/6. The probability that a student who buys lunch also buys dessert is 1 out of 6. Let's go ahead and wrap up this video. All right, there was a lot in this video. We learned how to determine if events are independent or dependent and how to find the probability and conditional probability depending on whether or not it's independent or dependent. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.